Artificial intelligence, or AI, is a huge part of today's world, and certainly a huge part of the future. There are lots of applications for AI. In fact, there are several different classifications of AI, and it's worth understanding those so that you can see just how far reaching AI goes. One classification of AI is called assisted intelligence. Assisted intelligence is a useful AI implementation because its purpose is to help to improve what people and organizations are already doing. Basically, assisted intelligence is about automating basic, repetitive tasks, like machines and assembly lines. Another classification is augmented intelligence. Augmented intelligence is about supporting decisions people and organizations make with the information that they have. A common example of this is online stores using analytics to predict what customers might want to buy. And then there's autonomous intelligence. Autonomous intelligence involves machines that review all kinds of real-time data and make decisions on their own. Probably the most obvious example of autonomous intelligence is the self-driving car. As humans, we have lots of different ways to learn and acquire intelligence. We can go to school, learn from our peers, watch videos online, read books, and so on. Well, AI isn't born smart either. It also needs to learn, and there's lots of ways for AI to learn. For example, machine learning is a way to create a computer model that's able to make predictions, or at least infer conclusions from data. Imagine having a patient database and being able to predict from that information whether the patient is or is not diabetic. Expert systems are a way to solve problems in a specific domain of knowledge. And meanwhile, neural networks are actually based on biological systems, and that's super neat. Neural networks actually learn from observation. It's a bit like machine learning, except you don't really know what you're looking for. Another way for AI to learn is something called deep learning. Deep learning includes ways to learn data representations. An example of that would be image recognition. Now, naturally, AI has lots of practical purpose. It's not just a fun exercise for programmers and math geniuses. There's real-life uses for AI. For example, AI can be used to predict intrusion risks, and that means that AI can monitor and evaluate systems to potentially determine soft spots, detect intrusions, and defend against security breaches should they occur. And on the topic of security, AI can include event responses, which means that AI can provide support for prioritizing security alerts. Even more, in the event of a breach, AI can help with performing the all-important root cause analysis, so the soft spot can be found and mitigated. Now, it's worth noting that there is such a thing as explainable AI, too. Now, this refers to types of AI where the results of the solution can actually be understood by humans. For example, imagine a database of cars, and we have some AI that predicts the price of the car based on information associated to that car. Once an algorithm is determined by AI, the mechanism can be explained back to the humans. Now, we as humans have been working in a technology field for a long time now. We've gotten pretty good at defining the rules of the game and developing processes for managing situations and everyday mundane activities. Now, with AI, we can start to apply those learnings and processes and start to implement AI for those practical purposes. And this is particularly true in the security side of things. For example, in the IT world, we do a lot of management to catalog users, devices, machines, and applications. AI can be implemented to manage all of those assets with a specific focus on cataloging and controlling which assets have access to what information. Assessing and finding threat vulnerabilities and determining likely attack vectors is a very difficult job to do, but it's also necessary. Now, having AI can help make this a much easier undertaking. And of course, AI can be implemented for security control verification to determine which security controls are available and where gaps might exist in the current security architecture. And that can free up humans to spend time shoring up security holes versus finding security holes. Now, AI is already in use today. This isn't a theoretical thing that we might have one day in the future. Some of the world's biggest organizations have adopted and adapted AI in some of their most popular and important findings. For example, did you know that Google uses machine learning to filter spam or security compromised emails? It's true. Google has one of the most advanced email features in the world, and it's all thanks to AI. Now that sounds pretty good for a free service. Now, IBM's Watson has also become almost a household name. But at this point, it's also synonymous with AI. Watson is a cognitive learning platform and can answer virtually any question, even if it's presented in natural language. I wonder if it knows the answer to life, the universe, and everything. And finally, there's Juniper Networks. Juniper provides networks that can use artificial intelligence to adapt to demand, meaning as there's more load on the system from more users, applications, or even just data flow, Juniper Network can adapt to that load and route traffic in the most optimal way possible. Machine learning is actually one of the most common implementations of AI. There are actually four main categories or techniques of ML. Specifically, the first and probably most common technique is supervised learning. Supervised learning involves teaching machines how to arrive at the right answer by using what's called labeled data. Next is unsupervised learning. Unsupervised learning is actually more about teaching machines to identify patterns in data and to learn how to categorize and label data itself. And then there's the hybrid semi-supervised technique. Semi-supervised machine learning uses, unsurprisingly, both labeled and unlabeled data to arrive at some answers. And finally, there's reinforcement learning. Reinforcement learning is about arriving at answers through the process of trial and error and which actions provide the maximum benefit. So let's dive into these techniques a bit. Probably the most common machine learning technique is supervised learning. So what is that? Well, supervised learning is all about using data that's already labeled in order to train a learning algorithm. With a supervised technique, the idea is to give an input dataset that has all the information about items that you care about. But the important feature of that dataset is that it also already includes the correct answers that you want ML to give you as the output. You see, with supervised machine learning, we're trying to train an algorithm by using actual, already known, and correct information. There are actually several methods of supervised learning, too. The most common are classification, regression, prediction, and gradient boosting. But at the end of the day, the main objective of a supervised learning technique is to be able to predict patterns and labels based on patterns and labels that you've seen before. For example, imagine you had a database of cars, and in that database you have all sorts of information about those cars: horsepower, number of doors, miles per gallon, and so on. Imagine you wanted to be able to predict what the price of a car would be based on that information. Well, using a supervised learning technique, I could feed that database into ML along with already known prices so that ML could determine a useful algorithm for predicting a price. It would compare its results to the actual prices and tune its algorithm to get as close to accurate as possible. Then, once satisfied, we'd have a model that we can use to predict future prices for future cars. Another pretty common machine learning technique is unsupervised learning. As you can imagine, it's almost the opposite of supervised learning. In fact, unsupervised learning is all about using data that has no labels at all. In other words, we have no idea what the right answer is. The algorithms for unsupervised learning scenarios are generally about finding patterns in the data and then grouping that data based on those patterns. These groups are sometimes called clusters. In fact, you might sometimes hear the term clustered machine learning as being synonymous with unsupervised learning. The purpose of unsupervised learning is to group data by similarity or to look for patterns in data that suggest anomalies. In fact, one of the clusters of data can be simply that: anomalous data. For example, imagine you had a database of penguins, and in that database you had all sorts of information about those penguins: flipper length, culmen depth, color, and so on. Now imagine you wanted to be able to group these penguins into three logical groups. What would that grouping be? Color? Species? Height? Well, with unsupervised learning, the whole point is that you don't actually know what a logical grouping is. So you can apply this technique to look over your thousands of penguins and then decide what an appropriate clustering would be if you wanted three groups. The next machine learning technique is semi-supervised. Semi-supervised learning actually makes use of a small amount of labeled data and then a large amount of unlabeled data. Common implementations of semi-supervised learning are classification, regression, and prediction. You might wonder why such a scenario exists. Well, consider the scenario where we want to have supervised learning, but having fully labeled data just isn't practical. We might have some, but not a lot. We've got other data, sure, but it's not completely labeled and it should be mostly relevant. The most common reason that semi-supervised learning is used is simply just when labeled data is expensive to get your hands on. And finally, we have reinforcement machine learning techniques. Reinforcement learning is all about using trial and error to arrive at the correct result. In fact, this type of ML is used in robotics, navigation, and gaming. With reinforcement learning, there are three primary components: the agent, which chooses to maximize the rewards; the environment, which is what the agent interacts with; and the actions, which is what the agent can do. The goal with reinforcement learning is to figure out the best policy that maximizes the expected reward. A common example is this. Imagine you're looking down on a simple racetrack in a figure-8 configuration. Now imagine you put a single car on the track and tell AI to drive around the track without hitting the walls or going in the wrong direction. Well, the first thing it will do is drive straight into a wall. And that's actually good. That's an error condition that tells it, okay, I can't do that, so I better try turning. And then it will turn, but then it'll go backwards. So that's no good. So it'll turn a little bit, but that's not enough. So then it'll turn a little bit more, and it'll make the corner, but it doesn't stop turning, so it runs into another wall. And on this goes. AI will just keep smashing into walls, but it will learn with each failure. And eventually it will figure out everything about driving that track. It'll know how to turn, what speed to drive at, what line to take to maximize its speed, and so on. Machine learning is already all around us. There are some key types of machine learning that you can implement yourself. For example, anomaly detection is a very common method that's been implemented for detecting unexpected system behaviors or outright errors in systems. Computer visions is another method of machine learning that can be used to interpret the world through images and videos. And something that's becoming more and more ingrained in our society is natural language processing. This is a method to interpret written or spoken languages. So instead of speaking to your phone in broken speak like, "Hey Siri, call mom mobile," you can speak more fluidly by saying things like, "Hey Siri, call my mom on her mobile." In fact, conversational AI is a method for fake software agents to engage in conversation. Think of times where maybe you've wanted to get help from some vendor or utility, and you end up in a text message exchange. Well, in a lot of those cases, it's actually AI that you're talking with. Let's quickly talk about the principles of machine learning. The first principle is representation. Representation refers to understanding how you could logically display the knowledge you have. For example, decision trees, graphical models, neural networks, sets of rules, and support vector machines are all ways that you could represent your data. The next principle is evaluation. Evaluation is all about, well, evaluating how well the model or algorithm is doing. Evaluation typically includes information like accuracy, prediction, recall, squared error, probability, posterior probability, cost, and margin. And then we have optimization. Optimization is all about enhanced data or algorithms to help the model get a better score. Now remember, when it comes to machine learning, there are generally four main categories or techniques of ML. Specifically, the first and probably most common technique is supervised learning. Supervised learning involves teaching machines how to arrive at the right answer by using what's called labeled data. Next is unsupervised learning. Unsupervised learning is actually more about teaching machines to identify patterns in data and to learn how to categorize and label data itself. And then there's the hybrid semi-supervised technique. Semi-supervised machine learning uses, unsurprisingly, both labeled data and unlabeled data to arrive at some answers. And finally, the reinforcement learning. Reinforcement learning is about arriving at answers through the process of trial and error. Which actions provide the maximum benefit? When we embark on our machine learning journey, we're really talking about using and manipulating data sets. Obviously, we need data for learning, but there's other data sets that we need too. For example, the most obvious kind of data set we need is a training data set. Training data sets are used during the learning process to help build a model and ultimately program the machine learning engine. But how can we know that our training is any good? Well, that's where validation data sets come in. A validation dataset is used after a model has been trained to compare the trained algorithm to more known data. A validation dataset is generally used to fine-tune parameters of a model algorithm. Even after a validation dataset, there's a test dataset. Test datasets are used as a sort of gold standard to determine the actual performance of a fully built model. And while we're training models, data is key. The more data you can feed a model during training, the better. For example, if you tried to train a model to predict the age of a person but only fed it one picture, it's likely not going to be very good at making predictions. But if you fed it 1,000,000 pictures, it'd be much better, wouldn't it? So one objective is always to find ways to make sure that you can provide data for ingestion into the model training. Data ingestion is really about receiving or importing data into storage, such as databases or a data store. Data can be streamed in real time, or it can be processed in batches. And of course, automated processes can be used to ingest and transform large amounts of data. So let's talk about that a bit. If you've ever worked in a raw data set, you know that it can be, well, a process. Data is not always in the right format, or it's not even complete. So when we're talking about bringing data into a model, there's really a typical process that you have to follow. For example, first there's data collection. Data collection usually involves gathering data from some relevant source. Now this could be CSV files, JSON structures, or even XML. Then you need to explore the data and figure out its features and its profile. And that means analyzing it for patterns, outliers, incorrect, inconsistent, or even skewed data. And third comes data formatting. This usually involves transforming the data into something that your machine learning model can actually use. Next, we have enhancing data quality. And what we mean by that is identifying problems with the dataset and then resolving them. Examples are incorrect data, missing values, extreme values, and outliers. And then there's feature engineering. That means converting the data into features that represent patterns to the learning algorithm. A common example of that is normalization. And finally, we can prepare the data by splitting it into training and evaluation datasets. That's right. A single, fully formed and prepared dataset can be split into two parts. One part, usually the bigger one, is used for training, and the remaining part is used for evaluation. Let's talk about labeling data. Understanding how or even if your data is labeled is key to choosing what sort of machine learning technique you're going to implement. But before we get to that, let's do a quick recap of what the four main techniques of ML are. The first and probably most common technique is supervised learning. Supervised learning involves teaching machines how to arrive at the right answer by using what's called labeled data. And next is unsupervised learning. Unsupervised learning is actually more about teaching machines to identify patterns in data and to learn how to categorize and label the data itself. And then there's hybrid semi-supervised techniques. Semi-supervised machine learning uses, unsurprisingly, both labeled and unlabeled data to arrive at some answers. And finally, there's reinforcement learning. Reinforcement learning is about arriving at answers through the process of trial and error. Which actions provide the maximum benefit? So as I said, when we talk about data in a dataset, that data can be labeled or unlabeled. But what does that mean? Well, first of all, labeled data really just means that it's understood and contains the answers you're looking for. Pretend for a moment that you had a database full of pictures of dogs and cats. Well, by identifying a certain picture as being a cat and another one as being a dog, it means that your data is labeled. Put another way, it means that the data is tagged. It's also important to note that data can have multiple labels. It's not just a dog or a cat, it's also an animal, and so on. A key aspect of tags and labels is that they're informative. It's not just some metadata, it's key information about the data that we're seeing. In fact, labels are so important, it's generally what machine learning is trained to determine. Why? Well, because getting labels from humans requires getting them to make judgment calls about data, and that is expensive. I mean, consider that database of dogs and cats again. Imagine if that database had 1,000,000 pictures in it. It'd take quite a bit of time for a person to walk through all of those pictures. Now, labeled data is generally used by supervised learning, and it's also usually predicted by supervised learning as well. And since semi-supervised learning is a hybrid of supervised learning, we know it uses labeled data too. So what's unlabeled data then? Well, unlabeled data is the opposite of labeled data. Unlabeled data is simply data that is not tagged. Unlabeled data is used by unsupervised learning and by semi-supervised learning as well. Generally, labeled data is used for pattern detection and clustering. So let's run through an example so that we can see exactly what labeled versus unlabeled means. Consider this image here. In the left column, we're seeing labeled data. What makes it labeled? Well, it's considered labeled because we know something about every item in that column. Importantly, the thing we know is all related. In this case, we know the type of entity. The top two entities are people, and the bottom two entities are robots. In the middle column, we're seeing the same dataset but labeled differently. In this case, every single entity has a different label, but they're all related because they're all the color of the entities. If you had said that the entities were person, yellow, robot, and light blue, that would not be a very useful labeling system because the labels aren't related. Remember that for a label to make sense, it has to be something that can apply to everything in the dataset. Then, in the right column, we're seeing an unlabeled dataset. Now, we as humans can see that dataset and we can infer some logical labels like round versus square, person versus robot, mouth versus no mouth, colors, and so on. But recognize what we did there. We looked at the data and we started to categorize it through analysis and grouping. We don't know what the labels are or even could be, so we're trying to figure that out. And that's what unsupervised learning is all about, figuring out the labels. When we're working with labels in a dataset, it's important to consider their accuracy and their quality. But what does that mean? What's the difference? Well, first, accuracy measures how close to the truth the labeling of an entity is to reality. If you were to look at a single item, you could describe that item very accurately. That would be considered the ground truth of that item. The accuracy of a label is how consistent it is with the real world. Accuracy often applies to computer vision, natural language processing, and other ML models that must abide to a certain immutable reality. Meanwhile, quality measures the accuracy of the entire dataset. That's right, if accuracy generally refers to a single item, quality refers to the entire dataset. The point is to ensure that the labels in the dataset are consistent across the entire dataset. So remember our example from earlier of labeling an entity as a robot and another as yellow? That would be a poor quality label. However, remember that you can have multiple data labels and maintain quality, as long as labels are consistent with each other. So you can say that an entity is of type person and color yellow, as long as every other entity in the dataset has a type and color label too. So how would you go about measuring the quality of the labels that were set or predicted by machine learning? Well, first you can measure the output labels against some sort of gold standard. Ultimately, what that means is that each entity that you feed into the model has a known correct answer, so you can confirm that the model generated labels that matched the correct answer. Another thing you can do is extract a sample from the model's output and have it be reviewed by labelers to determine if they would have given the same labels as the model did. And one thing that's sometimes done is to search for a consensus. A consensus is when multiple models work on the same dataset and output the same answers, or at least the majority of the models output the same answers. And lastly, there's what's considered an intersection over union. What that means is that a consensus model is combined with people and automation to compare their bounding boxes. When we talk about data in a dataset and how it's going to be understood by a machine learning algorithm, we often refer to the features of the dataset. Features? What does that mean? Well, features are actually individual characteristics or measurable properties of an entity in the dataset. Consider a dataset that had pictures of dogs and cats in it. We could look at each dog and cat and we could describe the features of an animal. If those characteristics were included in the dataset, then those would be considered features of the dataset. It's crucial in machine learning that the features that are given in a dataset are descriptive, distinctive, and independent. Arbitrary or insignificant bits of information can have a negative impact on machine learning algorithms. And features can be almost any type of data. They can be numeric, strings, or even graph values. So let's go over a few algorithms that we can use to select good features for a dataset. The first thing that we can do with a dataset is to use a filter method. Filter methods choose features from a dataset without any care as to the machine learning algorithm that's ultimately going to use it. The reasoning behind that is because that would mean that the dataset could theoretically be used by any machine learning algorithm. Effectively, if there is the chance that multiple completely different machine learning algorithms are going to use the dataset, the filter method might be the right choice. Next is the wrapper method. The wrapper method is kind of fun because it determines which subset of features to keep by using what's called greedy machine learning algorithms. And that finds the best combination of features that ultimately generate the best model outputs. So pretend you had one model that predicted whether a patient is diabetic based on all sorts of information. But then you found that the model was more accurate depending on whether a certain feature of that dataset was present or not. And that's what the wrapper method would figure out for you. Then there's the hybrid method. You can tell from the name that the hybrid method chooses features based on a combination of the features figured out by other methods. And like the wrapper method, it then figures out which combination derives the best model output. Another feature selection algorithm is the embedded method. The embedded method performs feature selection while the model training is actually happening. Embedded methods are very common and oftentimes preferred because they're fast, generally very accurate, and much less prone to overfitting. And finally, it's worth noting that there are many other feature selection algorithms out there too. For example, some of the other advanced methods include dimensionality reduction, genetic algorithms, permutation importance, and deep learning approaches. At the end of the day, the most important thing for your model training to be successful is to have verbose, complete, but also concise data. It needs to be feature-rich, but also limited to just what the model truly needs in order to determine a useful output. So what are some various techniques for figuring out which features should be used and which features should be tossed? Well, the first way is to look for high correlation. For example, imagine you had two columns of information in a database. Updates to one necessarily mean updates to the other. That would mean that having one column versus the other wouldn't add any additional or useful information to the model, so really only one of those columns would be needed. You can also look at a feature's p-value. Now, based on the p-value, you can determine if the feature has any real significance towards the work you're trying to do. For example, if you're looking to predict whether a patient is diabetic, their favorite TV show is unlikely to be a useful feature. Forward selection is another technique that you can use. Forward selection makes use of stepwise regression, and then once again, features are added based on their calculated p-values. Now, if we have forward selection, then we also have backward elimination. Backward elimination involves stepwise feature selection again, but starts with a model that has all the features and removes those features one at a time based on the calculated p-values. Another feature selection technique is recursive feature elimination. What a mouthful! Anyway, recursive feature elimination is all about selecting the exact number of significant features by using a rank-based system. Next is variable importance. The idea behind this feature selection technique is to determine the importance of individual variables using charts, like the random forest classifier, light gradient boosting machine, and XGBoost. And finally, there's regularization. Regularization is used to monitor the difference between bias and variance. For example, there might be a bias if certain values are very large, or if differences between values are very large, particularly when compared to other features in the dataset. For example, with a car, you can have an RPM feature and you can have a miles per gallon feature. Now, RPM is measured in the thousands, while MPG is measured in the tens. So there might be a bias towards RPM when really MPG can be the more important feature. With respect to machine learning algorithms, it really boils down to three main categories: regression, classification, and clustering. So let's take a moment to talk about regression algorithms. First of all, what is a regression algorithm? Primarily, a regression model is a type of machine learning that's used to predict some value based on various features of that item. Importantly, the value you're trying to predict is always a number. For example, let's assume that the item we're talking about is a car, and the value we're trying to predict is its price. We can use the various features of a car to determine an algorithm for predicting that price. For example, you could apply features like horsepower, number of seats, engine size, miles per gallon, and a whole host of other features to decide what a likely price is for that car. Regression analysis is a type of predictive modeling that calculates the correlation between dependent and independent variables. In other words, how do all these features of a car ultimately correlate with its price? Another aspect of regression algorithm is that the prediction always falls somewhere on a continuous spectrum. In other words, it's a number. Put in plain English, a regression algorithm is typically used to answer the basic question of how much or how many. Now, it turns out that saying something is a regression algorithm is a pretty vague statement. There are actually quite a lot of different types of regression algorithms that can be used to predict things like how much and how many. So let's go over some of the regression algorithm types. First up is the decision tree regression. Decision tree regression creates regressions or classification models by breaking up input datasets into smaller sub-datasets into the form of a tree with decision nodes and leaf nodes. The model then works through the tree, making binary decisions to ultimately arrive at the correct answer. Then there's the neural network regression. Neural network is usually used for classification problems such as handwritten digit classification. It's also quite often used for custom regression implementations and is more in line with biological methodologies. Next is the lasso regression type. Lasso is a form of a linear regression that applies shrinkage against a dataset. Basically, data values are shrunk to a central point. Generally, you use a lasso regression for making true predictions versus inferences. Another regression type is the ridge regression. Ridge regression is very similar to lasso regression, and they're sometimes even confused for one another. Ridge is a method for analyzing multiple regressions, and like lasso, ridge regression is good for making true predictions versus inferences. Then there's elastic net regression. This is actually a hybrid of lasso and ridge regression techniques. And next is the linear regression. Linear regression is likely the single most common regression algorithm because it's the simplest to understand and implement. Effectively, linear regression is a method for modeling the relationship between dependent and independent values, and you'll notice that that's effectively the very definition of regression. Another regression algorithm type is the polynomial regression. Polynomial regression is a form of regression analysis where the relationship between the independent variables and the dependent variables are modeled to an nth degree. Then there's the stepwise regression. Stepwise regression is a form of fitting regression models where the choice of predictive values is actually automated and determined on the fly. And finally, we have logistic regression. Logistic regression is used to determine the success or failure of an event. So we've gone over a few of the different regression algorithms, and there's actually even more than just that. But the real question is, how do you go about choosing one? What's the best regression algorithm to use? Well, the main thing is that the regression algorithm is heavily dependent on the data that it's fed. So it's critically important that you understand your dataset before you choose a model. Would it make sense to feed a bunch of pictures of dogs and cats to a regression algorithm? Well, clearly not. But how do I know if a dataset describing cars versus a dataset describing penguins should have one regression algorithm versus another? Well, the first thing you have to do is explore your data and understand it and all the relationships and impacts of each of the variables within it. Then you need to determine the goodness of fit between the various algorithms and the data itself. To determine the goodness of fit for a particular model, you can gather statistical metrics like R-squared, AIC, BIC, and error term. Then you can analyze these metrics to determine if that particular algorithm is any good with your dataset. Now also keep in mind your objective for the dataset. Depending on what you're trying to predict, certain algorithms are just better than others. For example, some algorithms may even return similar outputs, but one is just way easier to use given your dataset. Another thing to keep in mind when selecting the right regression algorithm is to use cross-validation. Cross-validation can be used to validate the differences between observed and predicted values. Based on the accuracy of the predictions, you may choose to select a different algorithm. One tip is to determine whether your dataset has multiple confounding values. Confounding values are extra independent variables that can affect a prediction, and so you may wish to exclude them. In these cases, you definitely want to avoid using automatic algorithms. And finally, one last tip is that regression regularization methods such as lasso, ridge, and elasticnet are simply not good for datasets that have high dimensionality and multi-collinearity. With respect to machine learning algorithms, it really boils down to three main categories: regression, classification, and clustering. So let's take a moment to talk about classification algorithms. First of all, what is a classification algorithm? Well, primarily a classification model is a type of machine learning that's used to predict some category or class to which an item belongs. Let's assume, for example, that the classification we're talking about is diabetes, and whether or not a person is or is not diabetic. For example, you could apply the features of a patient, like age, weight, and blood pressure, and a whole host of other features to decide the likelihood that a patient is diabetic. In this case, the classification is diabetic or not diabetic. Classification algorithms use the training datasets to predict a class for each of the items in the dataset. So, for example, I may have a database of patients and I need to go through each patient in the dataset to determine if they are diabetic or not. And that would be a classification. In a classification algorithm, the training data is used to create better boundary conditions for deciding which class a particular item belongs to. Then, once boundary conditions have been determined by the model based on the items in the training dataset, then those boundary conditions can be applied to predict a target class for new data. When we talk about classification algorithms, it's worth noting that there are some very specific terms that are used. So before we go too deep, let's make sure that we go over some of these terms. First is the term classifier. Put in the simplest terms, a classifier is the algorithm that maps data to a specific category. Then there's a classification model. Classification model is what determines the answer for the input dataset given during training. The classification model is what will predict the classes for the new data you'll put through the system. And of course, remember that a feature is an individual, measurable property of a piece of data that's being observed. Now, it turns out that saying something is a classification algorithm is a sort of vague statement. There are actually several different types of classification algorithms, though it's worth noting that they usually break down into one of three categories. The first type of classification is the binary classification. Sometimes this is referred to as a two-class classification. Ultimately, a binary classification algorithm can only have two possible outcomes. An example of this is classifying a light switch as being on or off. Of course, if we have a two-class classification algorithm, then it stands to reason that we'll have a multi-class classification algorithm. And indeed we do. A multi-class classification quite simply is used when data could be classified into more than just two possible outcomes. For example, if you were to look at a database of dogs and cats, well then there would be a binary system because each item is either a dog or a cat. But if you add a hippopotamus to the mix, then suddenly there are more than two possible outcomes. So we're looking at a multi-class algorithm. Then comes the multi-label classification algorithm. In the binary and multi-class algorithms, a single data item can only have one possible outcome. However, with the multi-label classification algorithm, a single data item can actually belong to multiple buckets. For example, when we look back at our animal database, we would be able to not only classify those creatures by their type, but we could also have another label that says whether they're pets or not. So you could say that a hippo is a hippo and not a pet, and a house cat is a cat and is a pet, and a lion is a cat and not a pet. So now that we know the categories of classification algorithms, there are actually several different algorithms that we could implement. For example, with support vector machine algorithms, each item of data is plotted as a point in an n-dimensional space, where n is the number of features, with the value of each feature being a value of a particular coordinate. Then lines are drawn between these features. In an overly simplistic way, the lines that best separate the groups of data into even distributions is considered the best way to classify the features. Random forest algorithms are an ensemble of learning methods that can be used for classification or regression analysis and use decision trees. Decision trees can be created on the fly at training time. And then there's the stochastic gradient descent algorithms. Now that's another mouthful right there. Anyway, these algorithms are really useful for large-scale learning such as natural language processing. And these algorithms are really quick and very efficient. One of the more common algorithms for classification is the logistic regression algorithm. This algorithm is generally used for binary classification of data points. It's actually generally used in the same way as a regular regression algorithm, except in this case, a specific outcome is anticipated for categorization purposes. Interestingly, logistic regression includes the hypothesis and sigmoid curve that can predict the outcome of an event. An example is to look at weather patterns and determine if it will rain or not. Naive Bayes' algorithm is a quick method to determine the classification of the dataset. This algorithm assumes independence between the features. It's useful for text classification such as spam filtering. In simplistic terms, a naive Bayes classifier assumes that a particular feature in a class is totally unrelated to any other feature. Another classification algorithm is the decision tree algorithm. This algorithm is used for prediction classifications. Basically, what happens with this algorithm is that the data is broken down into a tree structure, which then essentially generates a map for which the outcome is the result of the decisions. For example, imagine you wanted to predict whether a football game was going to be played. In that sense, your output is play or don't play. You could use a decision tree to ask all sorts of questions about the data and then ultimately arrive at that answer. Keeping it simple, you could base it on one decision. Is the weather good? But what decides that? Well, another decision, that's what. So you can have decisions all the way down. Ultimately, your dataset just includes information on attendance, weather details, compliance with rules, and so on. And finally, we have the k-nearest neighbors algorithm. This type of algorithm is used in supervised learning and can be used for pattern recognition, data mining, and intrusion detection. Basically, the idea is that we already know what the classification is, but we need the algorithm to look at the data and figure out what the algorithm is to arrive at the same conclusion. For example, I can feed this algorithm a database of patients and then have diagnoses as diabetic or not. Then the model can look at that patient information to determine the algorithm that arrives at the same conclusion. Now, with respect to machine learning algorithms, it really boils down to three main categories: regression, classification, and clustering. So let's take a moment to talk about clustering algorithms. First of all, what is a clustering algorithm? Primarily, clustering is a type of machine learning that's used to group similar items from a dataset based on various features of those items. Importantly, what you're trying to do is find a logical grouping for the items in the dataset. For example, let's assume that the item we're talking about is a penguin. What we'd be trying to do is group all the penguins in the input dataset into a certain number of logical groups. We can then use the various features of each penguin to determine an algorithm that can group those penguins into appropriate clusters. For example, you could apply features like flipper length, body mass, and a whole host of other features to decide what a likely grouping is for the penguins in the dataset. Now, clustering is an unsupervised learning technique and is often referred to as cluster analysis. What makes clustering algorithm unsupervised is the fact that it will use unlabeled data and try to determine logical groupings in that data. In a clustering algorithm, these logical groupings of data are more accurately referred to as clusters. Clusters are then used for downstream feature engineering or pattern discovery. When it comes to clustering algorithms, there are a few different algorithm classifications. For example, the first type of clustering algorithm is density-based. Density-based algorithms are quite simple to wrap our heads around. Basically, they're just groups based on high concentrations of data points that are separated by low concentration areas. So imagine you had a bunch of people go stand in a field. From an aerial view, you could look down and just pretend to draw a line and group people accordingly. Of course, the problem with that is that there's no real rhyme or reason to it other than density. So if we got another data set, we'd have to regroup people, but at least we'd follow the same principle. There's distribution-based algorithms. These algorithms group data based on the assumption that each item is part of a cluster based on the probability that they belong to that cluster. That's a pretty good algorithm to use. But as populations drift closer to each other, the probability that an item belongs to one cluster or another becomes less well understood and closer to 50-50. Then there's centroids. Centroids are the geographic center of a population of data points. Centroid-based algorithms separate the data based on multiple centroids in the data. And next there's hierarchical-based algorithms. These algorithms basically just build a tree of clusters. Then you can look at an entire branch and say, that's a cluster. For example, you could look at the phylogenetic tree of life and classify life hierarchically. Another clustering algorithm is the k-means clustering. This is actually one of the more popular mechanisms. So popular, in fact, that it's the only built-in algorithm provided by Microsoft Azure. Anyway, the k-means clustering algorithm is a centroid-based algorithm and truly is the simplest unsupervised algorithm. It tries to minimize the variance of data points in a cluster. And one thing about this algorithm is that it works best with a smaller dataset. Next, there's the density-based spatial clustering application with noise, or dbScan algorithm. The dbScan algorithm is a density-based algorithm. dbScan is actually quite useful at identifying outliers and working well with oddly shaped data. And that's important because when you're looking at data spatially, outliers can really impact the validity of a classification algorithm. Another clustering algorithm is the Gaussian mixture model algorithm. This algorithm uses Gaussian distributions to fix inconsistently shaped data and then calculate the probability that an item belongs to a specific Gaussian distribution. What this means is that the potential bubbles in which an item might live have been reshaped. Then the algorithm looks at the items to determine if they belong in the new bubbles. Next, there's the balance iterative reducing and clustering using hierarchies, or Birch algorithm. The Birch algorithm works quite well on large data sets. It's able to do that by grouping data into clustered summaries instead of the original data points. One of Birch's biggest advantages is that it can be used as an input to other clustering algorithms as long as those algorithms are designed to use data summaries. Another clustering algorithm is the propagation clustering algorithm. The propagation algorithm actually makes the data items send each other messages to identify sets of data called exemplars. But what's that? Well, exemplars represent clusters. So it's really useful for when the number of expected clusters is unknown. So imagine a bunch of random animal data. A piece of data is plotted spatially and says, hey, I'm a penguin and my flipper length is X. Then another piece of data says, oh hey, my flipper length is really close to X too. Can I hang out with you? And then another piece of data says, hey, I'm a dolphin and my flipper length is X. And suddenly the second data point says, wait, my flipper length is X just like both of you, but I'm a whale, not a dolphin or a penguin. Maybe I should have my own cluster. And next there's the mean shift clustering algorithm. Mean shift is particularly useful for image and computer vision processing. Mean shift is a hierarchical clustering algorithm that iterates over the data items and shifts them towards the mode versus the mean. And that's actually a key word here. In fact, this algorithm is sometimes referred to as a mode-seeking algorithm. Another clustering algorithm is the ordering points to identify the clustering structure, or optics algorithm. Optics is another density-based algorithm and is very similar to dbScan. Where optics is better than dbScan is that it can detect meaningful clusters even with varying density. It does that by ordering data items such that the closest items are neighbors. And finally, we have the agglomerative hierarchy clustering algorithm. This is another hierarchical clustering algorithm, but the differentiator here is that this algorithm groups objects based on their similarities and merges similar clusters until all the data points are part of one big cluster. And that means that the data is theoretically very simple to visualize. When it comes to machine learning, there are four main categories: supervised, unsupervised, semi-supervised, and reinforced. Probably the most common category of machine learning is supervised. So let's dive into that a little bit. One of the most distinctive qualities of supervised machine learning is the fact that the data that's used to train the algorithm is labeled. Remember that labeled data means that we know what it is. In other words, we're giving the algorithm the right answer so that it can tune itself. So when it comes to supervised learning, what we're really doing is passing in a data set of inputs along with the correct outputs. And that's what supervised means. Then the way the algorithm learns is by comparing the actual outputs that were given with the input data set to the predicted outputs. Then, if the error is too substantial, the algorithm is tuned until its predictions are more in line with the actual outputs. Then, supervised learning algorithms tend to use methods like classification, regression, prediction, and gradient boosting to predict patterns in data on additional unlabeled data. When we embark on our supervised machine learning journey, we're really talking about using and manipulating data sets. Obviously, we need data for learning, but there's other data sets that we need too. For example, the most obvious kind of data set we need is training data sets. Training data sets are used during the learning process to help build a model and ultimately program the machine learning engine. But how can we know that our training is any good? Well, that's where validation data sets come in. Validation data sets are used after a model has been trained to compare the trained algorithm to more known data. A validation dataset is generally used to fine-tune parameters of a model algorithm. But even after a validation dataset, there's a test dataset. Test datasets are used as a sort of gold standard to determine the actual performance of a fully built model. Now, alongside supervised machine learning, there's also the category of semi-supervised machine learning. So what's the difference? Well, semi-supervised machine learning actually makes use of both labeled and unlabeled data. In fact, semi-supervised machine learning usually uses a small amount of labeled data and then a large amount of unlabeled data. Then, just like with supervised machine learning, the algorithm tends to use the labeled data to train up a model and then use methods like classification, regression, and prediction to predict patterns and labels on the unlabeled data. So why do that? Well, the main reason is simply that labeled data is expensive to get your hands on. So that means that semi-supervised learning is much more cost-effective to use if you can't get enough labeled data. Now remember that supervised machine learning is generally based on the idea that we want to get answers to questions like how many or how much. We have an idea of the answers that we want to get. For example, if we have a database of cars, I know that I want a prediction on the price of each car. Or if I have a database of patients, I know that I want a prediction of whether or not each patient is diabetic. Now, when it comes to supervised learning algorithms, it usually breaks down into one of just a few types. For example, regression algorithms are probably the most common predictive algorithm. Regression makes use of training to predict a single output value. For example, if I have a data set of cars with all sorts of information about those cars, I would use a regression algorithm on the input data to predict the price of those cars. Then there's the logistic regression algorithm. Now this algorithm is generally used for the binary classification of data points. It's actually generally pretty similar to a regression algorithm, except in this case the specific output is limited to one of two possible states. For example, if I have an input dataset of patients, this algorithm can look for patterns in the data and determine if each patient is diabetic or not. And finally, there's classification algorithms. Classification algorithms use training datasets to predict a classification of each data item. This is actually very similar to the logistic regression algorithm, except that instead of only two possible output states, you can have any number of states. For example, if I had an input dataset of animals, the algorithm can look for patterns in the data and determine if each animal is from the land, sea, or air. Classification of data is extremely useful. Oftentimes, classification is a good first step towards feeding subsets of data into other models. You may choose to perform totally different algorithms on birds than you would against fish. So being able to classify data is extremely useful. Now, when it comes to classification, there's a few common types of classification algorithms worth noting. For example, one common classification algorithm type is the naive Bayes algorithm. It's a quick method to determine the classification of items in a dataset. This algorithm assumes independence between the features, and it's useful for text classification such as spam filtering. In simplistic terms, a naive Bayes classifier assumes that a particular feature in a class is totally unrelated to any other feature. The next classification algorithm is the decision tree algorithm. This algorithm is used for predictions and classifications. Basically, what happens with this algorithm is that the data is broken down into a tree structure, which then essentially generates a map for which the outcome is the result of the decisions. For example, imagine you wanted to predict whether a football game was going to get played. In that sense, your output is play or don't play. You could use a decision tree to ask all sorts of questions about that data and then ultimately arrive at that answer. Keeping it simple, you could base it on just one decision. Is the weather good enough to play? But what decides whether the weather is good enough to play? Well, in fact, it's another decision tree, and so you can have decisions all the way down. Ultimately, your dataset includes information that allows us to make those decisions all the way back up. And finally, with support vector machine algorithms, each item of data is plotted in a point in n-dimensional space, where n is the number of features, and the value of each feature being the value of a particular coordinate. Then lines are drawn between the features. In an oversimplistic way, the lines that best separate the groups of data into even distributions are considered the best way to classify those features. When it comes to machine learning, there are four main categories: supervised, unsupervised, semi-supervised, and reinforced. Now, we talked about supervised machine learning already, so let's dive into unsupervised machine learning a little bit. One of the most distinctive qualities of unsupervised machine learning is the fact that the data that's used to train the algorithm has no labels. In other words, it's unlabeled. Consider for a moment a dataset of things. As a human, you could look at that dataset and see that some of the things are robots and others are people. Some are green and others are yellow or blue. Some have legs and others have wheels, and on and on. Now, what you've done there is taken a nebulous dataset and applied labels. And that's what unsupervised learning does. Unsupervised learning algorithms determine patterns in the data so that it can figure out logical groupings for that data based on similarities. In other words, the main purpose of unsupervised learning is to group data into what's known as clusters. And it's worth noting that one of the common use cases for grouping data is actually to find anomalies. So what's a clustering algorithm? Well, primarily clustering is a type of machine learning that's used to group similar items from a dataset based on various features of those items. Importantly, what you're trying to do is find a logical grouping for the items in the dataset. For example, let's assume that the item that we're talking about is a penguin. What we'd be trying to do is group all the penguins in that input dataset into a certain number of logical groups. Now we can use the various features of each penguin to determine an algorithm that can group penguins into appropriate clusters. For example, we could apply features like flipper length or body mass, and a whole host of other features to decide what a likely grouping is for the penguins in the dataset. Clustering is an unsupervised learning technique, and it's often referred to as cluster analysis. Now, what makes clustering algorithms unsupervised is the fact that it will use unlabeled data and try to determine logical groupings in that data. In clustering algorithms, these logical groupings of data are more accurately referred to as clusters. And clusters are then used for downstream feature engineering or pattern discovery. So as I said, when we talk about data in a dataset, that data can be labeled or unlabeled. But what does that mean? Well, first of all, labeled data really just means that it's understood and contains the answers you're looking for. Pretend for a moment that you had a dataset full of pictures of dogs and cats. Well, by identifying a certain picture as being a cat and another as being a dog, it means that your data is labeled. Put another way, it means that your data is tagged. It's also important to note that data can have multiple labels. It's not just a dog or a cat, it's also an animal, and so on. A key aspect of tags and labels is that they're informative. It's not just metadata, it's key information about the data that we're seeing. In fact, labels are so important that's generally what machine learning is being trained to determine. Why? Well, because getting labels from humans requires getting them to make judgment calls about that data, and that's expensive. I mean, consider that database of dogs and cats again. Now imagine if that database had 1 million pictures in it. It'd take quite a bit of time for a person to walk through all of those pictures. Now, labeled data is generally used by supervised learning, and it's also usually predicted by supervised learning too. And since semi-supervised learning is a hybrid of supervised learning, we know it uses labeled data too. So what's unlabeled data then? Well, unlabeled data is the opposite of labeled data. Unlabeled data is simply data that's not tagged. Unlabeled data is used by unsupervised learning and by semi-supervised learning. Generally, unlabeled data is used for pattern detection and clustering. Now, unsupervised machine learning has lots of practical uses out there. So here's a few examples. Obviously, the most common use case is going to be to take a dataset and automatically group the contents into logical clusters based on their similarities. So imagine you had a dataset of thousands of penguins, but you wanted to put them into 3 logical groups for study purposes. You could use unsupervised learning to figure out what that logical grouping would be. Clustering algorithms like that are also incredibly useful for finding anomalies and unusual data. Because the algorithm naturally groups items, it will see outliers as being something that needs to be in its own cluster, thereby showing you things like fraudulent transactions automatically. Unsupervised learning also results in association mining, and that basically helps to identify groups of items that occur in the dataset. Importantly, it's associations that you may not even realize have existed. And lastly, one more use case for unsupervised learning is that it can be used for pre-processing of data in latent data models. Of course, unsupervised machine learning does have some disadvantages, and these are worth noting. For example, the results of unsupervised machine learning algorithms tend to have lower accuracy than supervised machine learning. And of course, that makes intuitive sense. Unsupervised machine learning has to figure out what the answer is from a random dataset, while supervised machine learning is trained with datasets that have the answer. Another disadvantage is that spectral classes don't always have a corresponding information class. And finally, since the data is unlabeled, time is required to interpret the labels that were given. In other words, the algorithm may determine that the data belongs in various logical groups, but then someone needs to figure out how that determination was even made. As you've certainly come to realize at this point, artificial intelligence is a very powerful tool. It can learn a lot and figure out things much quicker than humans can. It's an extremely useful tool that will benefit the world. But it also means that you have to use that tool responsibly, so we don't run into unintended and negative consequences. So how do we do that? For an AI algorithm to be reliable and safe, it's very important that fault tolerances are built into the system. This is especially true for situations where performance starts to degrade. It's also important for AI algorithms to have monitoring and logging built in. This will also help for performance and system integrity to be checked and regulated. And of course, the AI system needs to be able to fall back to the last best model or a simplistic heuristics model built using rules. If something breaks or starts giving faulty answers, that can cause problems downstream. If we can detect our AI is starting to do that, it's good to go back to a version that yielded better results. In the AI world, where we want to be the most responsible and safe are in systems that we call expert systems. But what's that? Well, put simply, an expert system is AI that's emulating the decision-making ability of a human expert. Then we want to put that AI in place of the human so that we can handle much larger scale. Expert systems offer the highest possible level of expertise because they emulate the human expert, but they can also provide that expertise in efficient, accurate, and imaginative problem-solving solutions. The response time for expert systems to provide solutions is generally considered reasonable and is, quite frankly, usually done in much less than the amount of time a human expert can do it. And because of the prescribed nature of their work, expert systems are generally more reliable than humans and prone to way less errors. Humans are complex creatures. We have the capability of thinking about many different situations and contexts and arrive at conclusions from lots of different avenues. So when we build AI into expert systems, there are lots of things that expert systems needs to do or be in order to be able to ultimately replace a human. For example, expert systems absolutely need to be flexible and be capable of adapting to change. There's one thing we humans are good at, it's throwing wrenches and curveballs into the mix. So if the expert systems can't handle those changes, then it won't be useful. Another thing expert systems need to be able to do is really just to have an effective method of utilizing the information that it contains. We as humans are going to interact with these systems and need to be able to consume the information that it gives us. If that information is too complex or incomplete, then it's not useful at all. And finally, expert systems need to be able to handle challenging decisions and devise effective solutions. Expert systems should not just work on simple and happy path situations. Oh, the patient has a high temperature? Well, then the patient likely has a fever. Well, thank you, I really didn't need AI for that. Now, expert systems are fantastic and truly a bright part of the future of this world, and there are lots of potential benefits to expert systems. First, expert systems can offer consistent answers for problems that are very similar. If you have a rash and then go to two doctors, then you may end up with two different answers, just based on different experiences. Well, expert systems have the benefit of all the experience and data that's ever been fed into it. So given the same consistent problem, it should provide the same consistent output. And of course, one of the biggest benefits of expert systems is that they can provide solutions to problems much more efficiently, particularly in the medical field. Now, one thing I like about expert systems is that they can be continuously improved. As we learn more, we can feed our cumulative experiences and information into the expert systems, and the quality of our decision making is therefore continuously improved. Now, since these expert systems are automated, they don't need to eat or sleep. They also have the benefit of a substantial amount of compute power, and that means that highly accurate answers can be given very quickly and at any time. And lastly, all of these benefits combine to make it so that solutions to problems, particularly complex problems, can be provided quickly, efficiently, consistently, and with accuracy. So obviously expert systems are fantastic and a big part of the future of the world, but that doesn't mean that they're not without limitations. For example, when a situation occurs that is out of normal, expert systems are not always able to be creative enough to devise a response. For now, we'll still need humans to handle those out of normal cases. Plus, expert systems rely heavily on the knowledge base that they've been given. If that knowledge base has incorrect data, then that can lead to wrong decisions. Now, since expert systems are automated, that means that they can be quite expensive to maintain. We're talking about people to feed the model, people to program the model, and then the actual maintenance of the infrastructure. So depending on the size of the market being served, that can be more expensive than it's worth. And finally, it's really important to understand that, at least for now, human experts are much better at being creative. That creativity is missing from expert systems. It's not just creativity in the solution, but also even understanding the input data and what it means. So as AI becomes more predominant in our world, people are going to get more and more uneasy. And that uneasiness comes from trust, or rather a lack of trust. AI can only be useful if people can trust it to do its job effectively and reliably. So how do we build up that trust? Well, quite simply, the answer is transparency. And how we provide that transparency is ultimately going to be based on the type of system that's being implemented. Deterministic systems are easiest to trust and make transparent because you can prove them. For example, pretend you had a simple method that adds two input numbers together. Well, we know that 1 plus 2 equals 3. So we can test our method by simply feeding 1 and 2 into it and make sure that the output is 3. With deterministic systems, the output is always verifiable given certain inputs. And that means that deterministic systems can be easily verified and thus made easily transparent by using unit tests, end-user tests, code reviews, and even just design documentation. Meanwhile, non-deterministic systems are trickier to make transparent. Generally, AI systems are all considered non-deterministic because they change and evolve over time and are based primarily on probabilities. So it's much harder to prove how correct they are. By their nature, they tend to be more opaque. But regardless, it's still important that builders establish the same level of trust in AI systems as their deterministic predecessors, and find ways to make the algorithms transparent and verifiable. AI systems need to make sure that they're fair and eliminate any bias that they might have, and that can help quite a bit towards proving their level of correctness. Effectively, for providing a mechanism for auditing and reviewing how the system works, you can build up trust to show how you came to that conclusion. Now, there are lots of stakeholders for AI algorithms, and each of them have a different benefit that they get from the transparency of an AI system. For example, if you can be transparent with end users, they'll have a better understanding of how results were arrived at, and so they'll have an increased level of trust. Try to imagine a system that takes some personal information and then diagnoses you as being diabetic. Well, you would be very interested in knowing how it arrived at that conclusion. With a doctor, you can get a second opinion, but with AI expert systems, it's almost like it's everyone's opinion. But you still want to be convinced, don't you? Meanwhile, the developers of the algorithm want transparency because it will make it much easier for them to debug, tune, and optimize the models. And of course, there's always project managers too. And PMs need the transparency because they simply need to understand how that AI system works so that they can talk intelligently to their own stakeholders about how the system works. Now, there's been lots of studies on building up trust in AI. IBM themselves have put together what they call the 4 pillars of trusted AI. And these pillars can help increase transparency and then ultimately increase the confidence in the AI systems. The first pillar is explainability. Explainability refers to knowing and understanding how the system works internally and how decisions are determined. The AI should be able to explain it to you, and you should be able to understand it well enough to be able to explain it to others. Robustness refers to the overall safety and security of the AI model and system. Really, we're talking about how stable and consistent it is. If I give the system information about a patient, and it says that patient is diabetic, and then I feed the exact same information in again, and it says the patient is not diabetic, then that's not a very robust system, and I'll lose trust in it. Now, fairness refers to removing bias from the model or the input dataset. This is particularly true for situations where the bias is a mismatch between the training data distribution and the desired unbiased distribution. Basically, you don't want to put data into the system that will skew the results. The final pillar is lineage. Lineage refers to being able to track and record the source of datasets, metadata, and models, and their parameters and test results. In effect, we should be able to audit everything about what generated the outputs. When you're designing an AI system, you want to establish or increase transparency in the system. One mechanism you can use is Google's model cards. The idea with model cards is to understand under which conditions the model performs best and most consistently. We want to understand its blind spots. One of the goals of model cards is to document the boundaries around the capabilities and limitations of any given AI model. Then, the actual performance of the AI model needs to be understood too. And this means determining which metrics and limitations derive the most meaning. And that's a key point. Which metrics are actually the ones that tell us how well the model is doing? Now, existing documentation can be used to determine what patterns worked best and what limitations exist. Then we can use that information to learn more and feed the new information back into the system to improve it. And Google also has a tool called Explainable AI. That tool can also be used to help increase transparency and confidence in the AI system. Explainable AI helps you to understand and interpret the predictions made by your machine learning models. The AI explanations tool can provide a score which describes how much each factor contributed to the model predictions. The what if tool can explore the performance of a model for a given dataset and help you derive an optimization strategy. And finally, the continuous evaluations tool can be used to take samples from trained ML models and compare model predictions with ground truth labels to enhance model performance. And all of that contributes to being able to explain your AI while simultaneously improving it. When we talk about responsible AI, one of the most important factors in that is privacy, specifically personal privacy. So as we embark on the journey of implementing AI solutions, it's critically important that the solution does not violate users' trust and commits to maintaining their privacy. The vast majority of consumer product services that are delivered on the cloud have features that make them vulnerable in ways most people aren't aware of. And AI systems are particularly good at being able to find and exploit those vulnerabilities. But just because you can do that, it doesn't mean that you should do that, which is what being responsible is all about. AI systems can be used to identify and track individuals across many devices. In fact, lots of AI is built specifically for that reason. But it's important that the collection of that information is anonymized so as to distort the line between personal and non-personal data. Again, AI can know which websites you specifically browse, but it should be more about what the majority of people tend to do, not what one specific person does. Another area of concern is that some AI systems are becoming much better at voice and facial recognition. And that raises privacy and security concerns too, because those systems could potentially be used by law enforcement agencies to search for individuals without probable cause or even reasonable suspicion. So, why do we care about protecting privacy? I mean, besides the obvious, where we want to keep our own information private and out of the hands of others, what's the bigger picture problem here? Why shouldn't we let AI be able to access that data? Well, one reason is based on predictions. AI systems can be used to predict someone's political views, ethnicity, sexual orientation, or even health based on all of this collected data. And then that information can be used against someone. Imagine not being allowed to vote because AI decided something about you. And another reason is profiling. AI systems can potentially be used to profile people by performing sorting, scoring, classifying, evaluating, and ranking people without their consent. Imagine being detained by law enforcement because AI classified you into some particular group. Of course, as responsible as you might be, there's always going to be some bad apples out there. The good news is that the governments around the world are putting laws into place to help protect the data rights of consumers. One example of that is the California Consumer Privacy Act, or CCPA. CCPA was created specifically to protect the data rights for consumers, and it boils down to four main rules. First, consumers have the right to know what personal information a business collects about them. As a user, you have the right to request that information from the business too. And that leads to the next rule. Consumers have the right to delete personal information collected about them. If you determine that the business has information that you don't want them to have, or you just don't want to use their service anymore, you have the right to make them delete that information. So why do businesses even have that information? Well, there's lots of different reasons, but sometimes the reason is simply because that information has monetary value. So your information can be sold. And that brings us to the next rule. Consumers have the right to opt out of the sale of their personal information. And finally, consumers have the right to not be discriminated against. If businesses are going to collect information about their users, then businesses are not allowed to prevent users from using their system based on certain information they collect. Obviously, there's exceptions like age-gated adult websites, but for the most part, if you want to buy a product from an online store, then they would not be allowed to reject that sale based on your political views, ethnicity, sexual orientation, or even health. Now, besides banking information, probably the most private information for users is their health information. People want their personal details about their health kept very private and confidential between them and the healthcare professionals that need to know. In response to that need, in 1996, the Health Insurance Portability and Accountability Act, or HIPAA, was created. The act includes specific entities. For example, healthcare providers who transmit healthcare transaction records electronically, meaning things like patient claims, benefit eligibility inquiries, referral authorization requests, and so on. Health plans such as health, dental, vision, and prescription drug insurers. Healthcare clearinghouses that process non-standard patient information. And business associates that use identifiable health information. Now, with HIPAA in place, all of the entities that are included in the Act are required by law to comply with a very strict set of rules and guidelines. For example, electronically protected health information must remain confidential, maintain integrity, and be available to appropriate entities when necessary. That means patients, doctors, nurses, and even insurers should be able to see the information when they need to, but no one else. Electronically protected health information must also be protected and safeguarded against any threats. So you can imagine how secure those systems must be. That's one of those situations where you'll end up on the front page of the newspaper for all the wrong reasons. Next, electronically protected health information must be protected against impermissible use or disclosures. In other words, if there's information in the files, they need to be kept private. So even if your nurse knows something about you from reading your file, it doesn't mean that they can just talk to anybody about it. And finally, workers must receive training and certify their compliance with HIPAA, so it's not just anybody who can access these systems either. So you can imagine that if we get AI involved in accessing these enormously private systems, there will need to be some serious privacy evaluation and trust buildup. As AI systems become more and more ingrained into our society, it's becoming critically important that AI should be designed to empower and engage everyone. AI should bring its benefits to all parts of society regardless of their physical ability, gender, sexual orientation, ethnicity, and so on. But what does that mean? Well, it means that we want to watch out for certain aspects that could cause our AI systems to be non inclusive. For example, representational harm is a real thing. This occurs when an AI system intensifies or echoes negative stereotypes, which can have a negative impact on groups of people and individuals. Another thing that can happen is opportunity denial. That can happen when an AI system is inherently biased and just completely fails to consider inclusivity when making its decisions. And then there's disproportionate product failure. This occurs when an AI system fails to work accurately for some groups of people or individuals due plainly to a simple lack of foresight and inclusivity. A fairly famous example of this sort of thing was an AI chatbot that was from just a few years ago. The AI learned from the internet and did not take certain factors into account. Basically, it learned from the most extreme examples rather than most inclusive examples. The result was an extremely rude and even racist chatbot that was taken offline very quickly. This was a very valuable lesson and one that we want to learn from. One of the ways that we can handle inclusion in AI algorithms is to manage bias in the various input datasets. For example, you absolutely want to avoid a biased data distribution. That happens when the dataset that's used for training the AI algorithms don't actually truly represent the population that your product or service will serve. For example, if you wanted to build a service that predicts optimal settings for F1 cars, it wouldn't make sense to only include input from NASCAR cars, would it? Of course, the inverse can be true too. Biased data representation happens when data that's collected favors a particular group, and so the model learns this bias from the training data. So if my service is going to be about all race cars, then only including information from NASCAR won't really serve rallycross very well. Another kind of bias is proxy variables. Now that can happen when data is strongly correlated with other data such as demographic data, which can create data bias. For example, imagine training self-driving cars but only using consistent, sunny, and dry conditions as your input. Those conditions result in correlations that are not necessarily accurate in different climates. And finally, there's the biased labels bias. This can happen if human labelers project their own bias when creating labels. Okay, so we know that we want to be inclusive and that biases can happen, but what do we do about it? What are some ways that we can improve our inclusiveness? Well, one thing that we can do is we can identify bias as a spectrum. Bias can be redefined as a spectrum instead of just focusing on the extreme outliers. In other words, there might be some information that sometimes leads to bias and sometimes not. Both can be valuable when building a model, so it's good to put that on a spectrum. Another thing that we can do is let customers actually be involved in helping to correct any bias that might be present within the organization. If your consumers feedback information like that, then you can take that information and use it to adjust the bias in your model. The good news is that AI systems will get smarter over time. That only happens as we feed them more information to learn from. So to help eliminate bias, we can cultivate diversity by feeding in different and more diverse data sets that AI can then learn from and label. Another way that AI systems can improve on their inclusiveness is to actually learn from past behaviors while considering present intentions. AI systems need to be developed to balance intelligence with the human desire to create and explore new ways of doing things. Just because we used to do something a certain way, it doesn't mean that that's what we would choose to do today. And finally, AI systems shouldn't just reflect the values of its creators. For the system to be truly inclusive and unbiased, the team needs to hire people from diverse backgrounds. So what happens if we don't design an inclusive system? I mean, what's the real damage there? So what if we exclude a small subset of our users? Does it really matter? Well, yes. Yes, it does. It really does. Let's walk through an example of a passport evaluation process. Imagine an AI system that's designed to confirm that a passport photo is valid. In the event that the photo is deemed invalid, the system will alert people that the photo does not meet passport photo standards for their country, and that could mean being denied entry. Well, at first that might not seem too bad. If a false positive occurs, then the photo is flagged as unacceptable when really it was acceptable. So the worst case scenario is that the photo is just retaken. But on the other hand, if the AI gives a false negative, then the photo is flagged as acceptable when really it wasn't. So the worst case scenario is much more severe. Now, that had nothing to do with personal agendas, sexual preference, or political views. The AI just simply didn't have adequate inclusiveness, and so it was prone to errors once it was opened up to a bigger audience. So, to identify inclusiveness issues like that, AI systems really need to be evaluated carefully to determine if there's any bias based on gender identity, ethnicity, or something else entirely. Now, obviously, you'll agree that AI systems should really treat everyone fairly. A good example of this would be an AI system that approves loan applications. A fair model would make predictions on whether or not the loan should be approved without incorporating any bias based on gender, ethnicity, or any other factors that might result in unfair advantages or disadvantages to any specific groups of people. But how do we do that? Well, one way is to minimize those biases by understanding and preventing the biases that result in unjust treatment of people based on their race, income level, identified gender, or any other characteristics that could be discriminatory. For example, if the models seem to deny women more than men, but then were much more even when gender was removed from the equation, then you know you have an unfair bias in the system that should be removed or accounted for. Now, social bias tends to be another bias that's unknowingly embedded in the training data. You really have to watch the data that's sent in for training to make sure that the algorithm truly comes to the correct conclusion based on the parameters you deem important versus parameters that can lead to bias. Another good way to reduce these biases is that AI systems should be designed to accommodate as many diverse perspectives and goals as possible to be able to predict classifications equally over all social groups. The more diverse the dataset, the less likely that there will be any accidental biases in the result. Ultimately, what we want to do is eliminate unfairness from our AI systems. Another term for that unfairness is AI exclusion. And as we've seen so far, the main way to eliminate AI exclusion or unfairness is to identify the different types that exist and what types of bias might cause it. For example, dataset bias is probably one of the more common types of biases. Dataset bias occurs when the various training datasets are not representative of the population base. Now, that can occur when the datasets have been generalized or anonymized, and so they simply don't factor in population diversity. The result is that the dataset itself has introduced a bias by simply excluding useful information. Then there's automation bias. Automation bias can happen when the automated decisions in AI systems override the concerns for social and cultural diversification. So, how does that happen? Well, remember that with AI, we're trying to train it based on information we know. So, we feed the AI a bunch of data and it builds algorithms. But during the training, the model may decide that certain data just isn't important, and so it's factored out. The result is that AI is not making decisions based on data that turned out to be important. Next, we have association bias. Now, association bias can happen when the training dataset appears to reinforce and even multiply a cultural bias against groups of people based on distinguishing characteristics. Basically, the idea is that decisions are being made on what may effectively be a coincidence. Using our loan example from earlier, imagine that we trained an AI system to decide whether people should be accepted for loans or not. Now imagine that the training dataset seemed to have a correlation that suggested that women tended to not be accepted. That means the AI may decide that gender is a factor in deciding whether someone should be accepted for a loan or not, whereas in reality, that may have just been a coincidence. Now, another type of AI exclusion that can happen is as a result of what's called interaction bias. Interaction bias happens when humans unintentionally tamper with AI systems and introduce their own biases into the system. For example, in my past, I built an AI system that would inspect wind turbine blades for damage. Now, we needed to train the AI to be able to tell what is and isn't damage. Sometimes we made mistakes and thought that an oil smudge was actually a lightning strike. So any mistakes given during the ongoing training of the AI would introduce bias that would result in oil smudges being identified as damage. And finally, we have confirmation bias. I mean, even us humans fall for this one, don't we? Confirmation bias happens when information is interpreted in a way that confirms preconceptions for a group or an individual. For example, we might be training an AI to make predictions and we give it the right answer, so it knows when it's getting close to a good algorithm. Well, it can still come up with an algorithm that comes close to the right answer, its preconceptions, even though it's interpreted the data incorrectly. So what happens if we don't design an AI system to be fair? Are there really any real consequences? So what if we're unfair towards a small subset of our users? Does it really matter? Well, of course it matters. For example, representational harm is a real thing. This happens when an AI system intensifies or echoes negative stereotypes, which can have a negative impact on groups of people and individuals. Imagine a system that actually does behave unfairly towards all women. That's just not right. Another thing that can happen is opportunity denial. And that can happen when an AI system is inherently biased and just completely fails to consider fairness when making its decisions. So imagine a system that works exclusively for rich people. Now, anyone who's not rich is not afforded an opportunity to participate in whatever the AI offering is, and that's not fair either. And then there's disproportionate product failure. This happens when AI systems fail to work accurately for some groups of people or individuals due plainly to simple lack of foresight and fairness. Okay, so obviously we all agree that fairness is important, and no one should be excluded based on biases in the model. But let's walk through an example to bring it home. Now imagine an AI system that's designed to filter age-appropriate books for children based on the title, description, and even its content. Books that don't match the filter are deemed invalid and the system will simply exclude it from the search results. So far, that sounds pretty good. Now, if the AI is not trained well and has any unfairness built in, you might run into a false positive. But that's not too bad. What that means is that a book that is appropriate is flagged as inappropriate and excluded from the list. So the worst case scenario is that the author or publisher gets upset and makes you change the algorithm. But on the other hand, if the AI gives a false negative, then that would mean that a book that is not appropriate is flagged as being fine. And now suddenly the worst case scenario is that the children can see some pretty inappropriate stuff in the search results, and you could get sued. Now, unlike inclusion, the issue here tends to be based on fairness bias. For example, there's lots of children's books that center on the LGBTQ community, but that term would be unfairly considered inappropriate. So to identify fairness issues like that, AI systems really need to be evaluated carefully to determine if there's any bias towards any gender identity, ethnicity, or something else entirely. So as we've been able to see so far in this course, AI can be very powerful and very, very useful. We can use it to make predictions, classify things for us, and even solve some very complex problems. But we've also seen that AI can be dangerous if unregulated. What that means is that we need to build accountability into the AI community. For example, companies need to understand their legal obligations when they embark on their AI journeys. This can be CCPA or HIPAA compliance, but it can also be based on local or even international laws too. But at the same time, companies should seek out and understand where their level of responsibility ends, since there's very little control over how clients will use their offering. Corporate AI inclusion and accountability policies should also be created. These corporate policies need to be concise and accessible to whoever needs them. Obviously, that includes the design and development teams that are responsible for building the AI, but it also really includes teams like labelers, PMs, and even testers. Now, I can't stress enough that when it comes to accountability, you should absolutely keep detailed records of your process, design, decisions, methodologies, and so on. Now, obviously, that can all be leveraged for future projects, but it can also be used to explain how the system works, why it works that way, and just even as a means to protect yourself. And of course, people should absolutely follow existing company product and inclusion guidelines, as well as understand and follow local, national, and international laws, regulations, and guidelines. It's not just the company that needs to follow those rules, it's beholden on all of us. Now, making sure that we remain accountable sounds good, but it's not without challenges. For example, some algorithms are written as a black box. Black box algorithms refer to the processes that may be perceived as being biased in the decisions that it makes. If someone challenges the company to explain how an AI works, and the system is a black box or even just proprietary, then that could make things really messy when it comes to accountability. Another challenge is with AI systems that need to collect large amounts of data, especially personal data like browsing habits. When systems gather that much data, there's always potential worry about misuse and thus mistrust. Think of how some people feel about Facebook. Lastly, one of the biggest challenges is when there's a lack of standards or guidelines. When teams are working on AI and they're doing it like cowboys, it's very difficult to explain the AI, what it's doing, or why, and good luck repeating the process too. The good news is that there's solutions to managing accountability of AI algorithms. For example, explainable AI, or XAI, allows for stakeholders like end users, developers, and PMs to understand the AI algorithms and provide guidance on the decision-making process. XAI means that the AI can be explained to the stakeholders well enough that the stakeholders can explain it to someone else. Another key solution to AI accountability is to build privacy into the solution from the get-go. Privacy by design drives the entire design process, and that's good because privacy really does need to be considered at the initial design phase of the project, because it's much harder to retrofit after the fact. And one more accountability solution is to use AI regulatory frameworks. Now, these frameworks are required to make sure that the AI systems are accountable and unbiased. It's all built right in. Now, of course, you can be compliant, accountable, and fair, but there are some bad apples out there. So to combat that, there are government policies that are specifically designed to protect and secure data. And probably the most famous policy is General Data Protection Regulations, or GDPR. With GDPR, companies are required to process personal data lawfully, fairly, and transparently. GDPR also requires companies to only collect, process, and store data that is necessary, and then delete it when it's no longer required. Another thing GDPR requires is that people have the right to ask companies what information they have about them. They're also allowed to request corrections or even deletion of their personal data. Now, with GDPR, written consent must be received from someone when the company wants to process the data beyond the original intent of what the data was collected for. And more than that, consent can be withdrawn at any time. Now, failure to abide by GDPR rules can result in extraordinary fines and sanctions. For example, British Airways broke those rules and were forced to pay £183 million. Now, in order to comply with GDPR rules, companies are required to conform to certain regulatory requirements. For example, companies are required to maintain a data breach register. Then the regulator and people involved in the breach need to be notified within 72 hours dependent upon the breach security level. Companies are also required and responsible for incorporating processes and procedures to protect personal data. They must build privacy into their systems. And on top of all of that, companies need to provide a data protection impact assessment. This assessment must be performed whenever a significant change is made to how the data is processed to make sure of the integrity of the changes. In other words, no bait and switch is allowed. Now, GDPR also requires the strict control of personal data. Whomever controls the personal data of a person must make sure that that data is safe and protected whenever it's being transferred outside of the company to any third-party processor or even internal entity. Next, GDPR requires that there needs to be a data protection officer. Now, this person must be assigned the responsibility and oversight of managing whenever the company processes large amounts of personal data. And finally, with GDPR, compliance training and awareness for relevant employees is required to ensure that employees understand and are aware of the GDPR requirements and their responsibilities whenever a data breach occurs. So in this course, we've examined the basics of machine learning and artificial intelligence for use in the Azure ML services. We did this by exploring using artificial intelligence and machine learning to solve business problems, data sets and how to manipulate labeled versus unlabeled data differences, using regression, classification, and clustering algorithms with machine learning, supervised and unsupervised machine learning models, reliability, safety, privacy, and transparency in AI algorithms, and security, inclusiveness, fairness, and accountability in AI algorithms. In our next course, we'll move on to work with the Azure ML Studio and learn about the features of some of those Azure ML services.